Hello everyone, and welcome back to the Technology of Beauty, where I have the opportunity to interview the movers and shakers of the beauty business. And today is no exception. Today I'm going to be interviewing Dr. Atta Behfar from Rion and also the Mayo. Thank you for joining me.
Pleasure to be here.
It's great to have you on the show.
Thank you.
We're here in San Diego, California at the Aesthetic Innovation Summit meeting 2022. And Rion, the company Rion, has made some presentations, and we're talking today about exosomes and regenerative medicine.
Yeah,
right?
Absolutely.
So tell us a little bit about yourself. You're a physician.
I'm a physician. I do heart transplant at Mayo. I've spent 20 years in the regenerative medicine research space, mostly focused on stem cells, but lately, over the last decade, we've changed our minds. It's the exosomes that are the active ingredient for regeneration.
Is it stem cells versus exosomes, or are exosomes part of the stem cells?
It's not stem cells versus exosomes. It's just that what's beneficial from stem cells is exosomes. What we realize, though, is that when you culture stem cells in a petri dish, make them grow, their tendency when they're really regenerative is to actually trap serological exosomes, actually platelet-derived exosomes. They grab them, and then when you try to use them clinically, it's those exosomes that they're releasing that incite regenerative events. So they're really recycling platelet exosomes from the petri dish to drive regenerative events. So when we saw that, we thought, why use this middleman? Why not just go to the source and just use the platelets?
That's interesting. So can the stem cell be thought of as sort of the courier that's carrying around the active ingredient, which is actually the exosome? Is that what really has the positive, the beneficial effect?
I think when you look at the literature, especially over the last, I would say, 5 to 10 years, the paracrine secretions, that's what's been called, of stem cells, is really now thought of as the active component. Well, what's in that secretion is the exosome.
Okay. So at Rion, switching gears a little bit, you provide the exosomes for various uses. Is that correct?
We're an exosome innovation hub. We licensed several technologies that actually came out of my lab at Mayo that really focus on derivation and purification of regenerative exosomes.
Now, you harvest or obtain these exosomes from platelets. Is that correct?
That's right.
Now, can your exosomes be injected into me?
Absolutely. So exosomes, and we've tested, as a transplant doc, I'm very careful about this. So we've looked at exosomes, and they don't appear to harbor self or non-self markers. So exosomes, unlike cells, are compatible across different individuals, and in large part across different species even. So we could put human exosomes in rabbits or pigs and look at how they work.
Okay, couple questions. Are there multiple types of exosomes?
Yeah, so if you think about the number of cells you have in your body,
right,
millions of different types of cells, each of those cells makes many different types of exosomes.
So they're specific. I have cardiac exosomes,
you have
skin exosomes, and so forth?
Absolutely. And all the different cells in your heart make different types of exosomes. All the different cells in your skin make different types of exosomes, each meant to do some very specific action. So when we hear the concept of exosomes, that doesn't equate regeneration, right? That just means you have a little particle that's shed by a cell. What we really focused on is which of these many millions of different exosomes actually can foster healing, right? That's what we're interested in. And so even from platelets, if you treat the platelets wrong as you're collecting these exosomes, you get things that we call toxosomes, inflammasomes, kilosomes, right? These are things that...
These are bad exosomes.
They're not bad because if you have a cancer cell, those are great exosomes.
Sure.
If you have an infection, the platelets do their job, they're great exosomes. But if you have a wound, they're terrible exosomes, right? So for the right reason, those are wonderful. For our use, which is in Reg Med, we really want a focus on a particular exosome, which we call the regenosome, or the regenerative exosome.
You said there's specific exosomes, say, for the heart, and even within the heart, for the different cells of the heart.
Yeah.
And yet you're telling me that you harvest these exosomes from the platelet. If you're harvesting them from the platelets, do you actually harvest exosomes from the platelet that could be used potentially in the heart?
Yeah, so the platelet regenerative exosomes do drive blood vessel formation. So when you're healing a wound, you need new blood vessels.
Sure.
Now think about individuals who may have had ischemic heart disease, right? So blockages, typically you can get bypass, you can get a stent, all's okay. But certain individuals have so much blockage, we really can't stent them anymore or bypass them. They need their own heart to rebuild new blood vessels, right?
Yes.
Biological bypass grafts. These platelet exosomes can do that for the heart. So just like they form blood vessels for the skin, now we can leverage that power and use it in a unique new way.
Would that fall into the field of angiogenesis?
So it would be angiogenesis or vasculogenesis. The way I think about angiogenesis is when your body is being formed as a fetus, you need to make all these blood vessels all over. When you actually have red blood cell containing blood vessels, I think about that more as vasculogenesis. I think so what we see with the exosomes, it's not just what you see with VEGF that drives angiogenesis and you get like a rat's nest worth of blood vessels.
Right.
You actually get a complement of signals, and it's a complex biologic, but there are agonists and antagonists built within these exosomes that drive all the key steps needed to form a functional blood vessel. And so what you see at the end of the day when you deploy these exosomes in tissues where you're getting wound healing, or if you're using them in the heart, is you see circles with red blood cells in them on histology.
Really?
So they're actually functional blood vessels.
How big are these molecules?
They're tiny.
How many kilodaltons would be a typical exosome?
So we typically measure them based on their diameter, and they're between 50 and 150 nanometers. But you could catch them easily on a 300 kilodalton filter.
Do you have any challenges getting them through the skin barrier and actually delivering them subcutaneously or intramuscularly or other areas besides the dermis, say?
So what's very interesting about platelet-derived exosomes is actually the same thing that's interesting about platelets. They're sticky, right? So when you get a cut,
that's a
they
good
all
thing.
stick, right? You want them to stay there. Those integrins are carried forward on the skin of the exosomes. And so when you put them in the muscle, if you put them subcutaneously, if you put them in the heart, they stick. If you put them on a tumor, let's say you load them with a chemotherapy, they stick there and they don't move.
Okay.
And so from a pharmacokinetic standpoint, as a drug delivery tool, they're very unique in that you can target them specifically to the area of interest.
So I get that they stay put.
Yeah.
But how do they get through the skin?
Oh, so what we've seen in the most recent PH study is that they actually can penetrate the strata, and we see them as deep as the reticular dermis, stuck on collagen, because collagen has integrin binding sites. And when we go back and look and track the exosomes, they're actually getting in through the pores. So you see the pore almost looks like a well at the bottom of exosomes, and then they get into the skin from there.
So they don't track through the hair follicle?
They also track through the pores, through any sort of any
adnexal.
Yeah, you can see them.
Surface or in the dermis, they follow that as a track?
They follow those as a track.
Interesting. Okay. Well, this is so exciting. There's so much to learn about rejuvenative medicine in general, but in particular exosomes. And I want to thank you for joining us today on the Technology of Beauty and for coming to AIS. I assume this is your first AIS.
This is definitely my first AIS.
You're a heart surgeon. You're here running around with guys like me who are aesthetic plastic surgeons.
Well, it's honestly, I think, a unique opportunity to combine forces and learn from each other.
Absolutely, I agree. Well, thank you very much. I look forward to having you back on the show. Thank you for joining us.
Pleasure.
Take care.
Take care.